Thanks for the introduction, Martina. Very nice. And I think this is one of the outcome of our collaborations as well, linking the observations to the modeling. So what I will be presenting here today is a compilation of different work that we did on that topic, some by our group, one by Atulya Saiprakash, who finished our PhD, who could not be here, but that will be our work. We'll try to summarize it as well as possible. So that will be work done on trying to understand the origin of the cirrus in particular that we are observing from satellites, and I'll focus this talk only on Lagrangian approaches. There we go. So I like to start with the motivation, which is this frustration, what I call here the observational frustration. That will be just going to the office in the morning and then looking at the sky, and you see this nice here ice clouds, and I even put a little contrail in there together with the cirrus, as Andreas showed 2 months ago. That is quite often the case, and we see that, and then of course I start thinking about like what is that, and why do these clouds look this way, and why are they here at this time? So of course you can look at the weather or start thinking a bit deeper, and usually I don't end up really understanding what's going on, but that's fine. I can just enjoy the sight, and that's good enough. But then I get to the office and I, in the end, do the same thing. So I'm looking at data this time, so much more data. I will be mostly talking here about satellite, even if you can apply this to anything. And you look at the satellite data, and there are only snapshots, and it will be the same questions. So here I gave an example of one case that I will be reusing throughout the talk for consistency. So this is a frontal cloud cyclone over the US. You have the radar reflectivity on top. So this shows you the profile here, the cut through the edge, well, through the center to the edge of the cyclone. And you see the cirrus on top that is well captured by the LiDAR backscatter. So here you already see the cirrus. So then you can already start wondering why that is. This case is quite easy, but still. Then you see the microphysics products. For instance, here on top, the ice water content. At the bottom, the ice crystal numeric concentration, so the amounts per liter here. And you see patterns in your products when you look at vertical profiles like this. So this is 60 meter resolution vertical. So you see these very nice structures. And you can also wonder there, why do you have more ice here than you have there, for instance? And all these questions are sort of a bit of the same as when looking at the sky, really. And then it gets worse as you're going towards level 3, which are just gridded data. So you take this, you put it in 1 by 1 degree, and you take averages over a season or a year here, grouping them by temperature bins, for instance, and you are losing more and more your information. So the question is, how can we go beyond the snapshots of what the satellite is seeing here? And to do this consistently between the microphysics product, the level 2, the vertical profiles, and the gridded data. So what approach can we do to do it? And this, of course, over a few years of data will be ideal. So first, we can define what information we will like to use. So that will be a good starting point. For instance, having the information on the ice cloud regime or the cloud regime in general that you can be looking at. So for instance, is it orographic or frontal or convection or something else? So there are already classifications out there, one very nice by Chris Peart et al. So I won't be talking too much about that, but this is one information of interest. The second will be the ice formation pathway. So by this, I mean, without going into all the details, really just saying if the ice that we're observing was formed heterogeneously or homogeneously will be already a great amount of information that we don't have. So by heterogeneously, I mean, did it form involving ice nucleating particles, or did it form homogeneously through supercooled droplets or aqueous aerosols? We could also wonder about the cirrus origin. So it's a bit different from the ice formation pathway, and that's a nice contribution here, a figure by Lutke et al., and nice contribution by Martina as well. Defining cirrus by either they formed in situ, so do they form in the cirrus regime below minus 40 degrees, roughly, or did they form with the help of liquid droplets? So do they have a liquid origin through an uplift of air mass from the mixed phase regime? And of course, you could add other things like the time since the cloud formation between the formation and the observation. That will be something that will be highly relevant to understand better the life cycle. What are the environmental conditions? This we have to some extent, but not always, meteorological, aerosol compositions, and so on. And if you think of anything else, I'm happy to also take any information that you will need. And of course, the motivation is that these metrics influence very strongly the properties of the clouds, microphysical, the extent, the life cycle, the microphysical properties, and then indirectly their radiative effects. And yeah, they are not really associated so far with most satellite observations. So that is our goal and the goal of the story I want to tell today. So starting on the left from the vertical profile or whatever typical observation you have, and associating with that together exactly like vertically resolved, in that case, the ice cloud regime, the formation pathway, for instance, the cirrus origin, time since formation, and whatever else metrics we would like to use. So that will be the end goal, the right, and that's where we start from on the left. There are many ways to do that, and for keeping it short, I will really focus here on Lagrangian techniques, so Lagrangian trajectory models. So these models were used very often to do this kind of analysis. This is not new, but mostly this focused on few case studies. You can have a campaign and you wonder where my cloud comes from. You can do some analysis, but it's not really do operationally. So really on a lot of data. Some modeling studies showed that applying these methods on a lot of data can actually be very useful to understand ice formation mechanisms. But yeah, this approach were not really done on observations. So that's what we wanted to see today. Is it possible to do it? So we started with a quite simple but very nice and beautiful approach by Vernley et al. Here. So they focused on the cirrus origin, so saying did it form in situ or did it form using liquids, droplets? So the approach is just you start at time zero here and you use a back trajectory. So you go back in time. The top figures show the ice water content and the bottom show the liquid water content as function of time. So you start here, the first two are identical, and you go back until your ice forms, so until you have no more ice water content. This is when your cirrus formed 48 hours ago. That's a long-living cirrus in that case. And you have to look then at the liquid water content. If you did not have any liquid at this moment, then the cloud is classified as in situ origin. If you had some, then it will be classified as liquid origin. So this relies, of course, on reanalysis to determine how was the state of the cloud back in time. There are some threshold used. I put a few here. They change from one study to another, but this is a good estimate. So we wanted first to just reproduce this along the A-train track. So just running for every pixel we have, just running the same approach. So we switched for that to FlexPart from their Lagrangian approach. I put some configuration detail. I will put many more after, but I won't focus too much on that. But the talk is recorded, so you can go back to that. So we used version 11, ERA 5 for the weather, the meteorology, 1 hour resolution. We used specific species, but there is no gravitational settling at the moment. So this is something to consider. One really great advantage of using FlexPart is that you release many particles. So you have 1 million released here per orbit, which is from equator to equator. I'll detail later, and we go 5 days back with 1 hour time steps. So this is how it works. We are first selecting some curtains, so I'll be reusing the same example as before. Then we are slightly regrading the data, but not by much because we want to keep high resolution for that. So it is just set 4 satellite pixels per grid point. And for each of these grid points, we will be looking if there is a cloud or not. So that already limits our trajectories. So we only run trajectories when there is a cloud. And for each cloud pixel, we'll be running FlexParts back in time, 5 days here, 1 hour resolution, as I mentioned. So time 0 is the overpass time, and then we go back in time. The advantage here of FlexPart is that we will run many particles, and the amount of particle that we are running per grid point is weighed by the ice crystal number concentration. So the more ice we have, and the more precision we want, so to speak. So we are running more trajectories to really include the spread. So yeah, we are coupling this with more information on the weather or on the cloud microphysics. This is done offline. So for each 1 hour time step, we have the liquid water content, ice water content, and we can run the Verni approach in the same way that I introduced earlier. So it's pretty straightforward. So this is the example for what I showed you before. So this is the time since formation. So this is the time since we are losing the ice water content in the reanalysis. So we are still relying on reanalysis with some few tricks that I won't have time to discuss now, but I'm happy to discuss them later if you like. So here you see some clouds are quite fresh, below 10 hours, and some are more aged. Here it's to close to 30 hours in the anvil here. And you see 2 areas that are fresh. There is the front here, which makes sense. Above the front is a bit more aged, so that's the air mass that was transported up. And you have a second area here that is more fresh. So then you could ask yourself why. And this can be explained you looking at the origin. So because we apply this method, we can see which part of the cloud formed in situ and which part formed through liquid origin. And so this part that was fresh here is actually from liquid origin. That makes sense. This is the warm air mass here that is transported up. And you have some area here where you probably had an increase in relative humidity where in situ formation was possible. So now we can start understanding a bit better what's going on in the profiles that we are observing. And we did that for 1 full year of data. That's 2010. So for Calypso Cloud Set, that's a good year. And we get, well, whatever profiles you could be looking at. So this is a zonal mean of the hours since between observation and formation of the clouds. And on the right will be the origin. So mostly in situ origin purely, so purely blue here on the very high up, which makes sense. And some liquid origin as you are going down, and you can see probably some orographic areas where you have peaks here that are showing a bit higher up. So I won't go too much in detail, but I'm happy to discuss again these plots. So yeah, we see also that most cirrus will be formed within 30 hours of the observation. That's already a high estimate, but that's consistent with what we are thinking. Yeah, so we could also look at horizontal maps. This is a bit more complicated because then you have a 2D view. So you have to decide not per pixel, but you have to decide for your overall cloud. So you have to define, is my at least cloud vertically? Or if you look just at the vertical area in the cloud, did it form 100% liquid origin or sort of a mixture of the both that is 50 to 100% or 100% in situ origin? So that I will be showing just after are more, is it purely in situ origin or is it mostly liquid origin? It's not fully, it's usually a mixture of both, but yeah, this is what we are observing. So most in situ origin here we are seeing in the tropics, that might be the TTL region that is showing here, some also in the poles, the high latitudes, and liquid origin that we're observing here will be in the mid-latitudes with a shift between the upper row that is December, so December, January, February, and here June, July, August. So you see a higher amount of liquid origin in the winters where the jets are a bit stronger, and the same in the south hemisphere. So a lot of interesting things. We are still looking a bit more in detail. So this is still preliminary, but that seems to look not too bad. And now that we have that, we can finally combine it with the satellite observation. So you can couple it with the microphysics retrievals, and you get these sorts of things where you can look at the profile, the red profile of ice water content, for instance, on the left, from the base to the top of the cloud. So that's the relative shape of the profile for, let's say, purely in situ cirrus in blue. That will be here, or mostly liquid origin, which will be there. So we can look at how the microphysics responds to the different origin. And yeah, that for now makes sense that the liquid origin will have, usually the clouds are thicker, so you can see it here. This is the geometrical thickness of the cloud, which is, well, let's say, we can look at the global one here, but it's thicker for the liquid origin than for the in situ, because we are just looking at more convective clouds typically. So you access to much larger data clouds. Sorry. So you can see here the profile that shows a bit more sedimentation, which is why the ice water content is growing a bit more. Yeah, but again, work in progress. So this remains a bit preliminary. So here, what did we learn? We learned that we could do that actually. It's quite efficient to run a full orbit. Takes a couple of minutes, I think 5 to 10 minutes maybe. So that's something that is accessible finally. This was a lot of work actually by Silvia Bucci to get this done, to get FlexPart running really quick on that. But I think we are at the stage where we can do this sort of analysis. We started to compare two satellite observations, and we find some expected behavior, but this is still a work in progress. And we want to include more things like the environmental conditions. We also want to add the sedimentation to the air parcels that we do not have included for the moment. Of course, there are a lot of issues. You have to trust Aero5 also, not only for the meteorology, but also for the ice cloud microphysics, which is something that we could, that it can be discussed. Some evaluations show that it's not too bad. Some show that it's not very good, depends on the regions also. We know large issues for the high latitudes, for instance. In the tropics also, RF data is not always great. The convection is not necessarily predicted at the same area, but it also lacking some very high cirrus TTL that we have to add by hand somehow. So we have some extra methods that I didn't detail here. And we do not have, with this method, access to the formation pathway. So we cannot say if the cloud formed homogeneously or heterogeneously, which is something that we wanted to know as well with our together with our satellite data. So that leads us to a second method that was developed. So this is the work of Atulia. And this involves one step further. It will be to combine microphysical model, Lagrangian microphysical model, to the trajectories. So we are switching now the model from FlexPart to CLAMS because, well, it was not developed for FlexPart, but we are changing the model, but the idea is still the same for each parcel that we're observing with the LiDAR and the radar. We are running a trajectory. The difference is that you don't only get the trajectory, but you are running a microphysics model on the trajectory. So this is how the framework is working. So she called it DCIs. So you start from LiDAR radar observation, just like before, and you go just like before, a bit back in time. So with FlexPart, we went 120 hours because we had no limitation, really, other than the speed. Here we are going to 12 hours because we don't want to go too far as we get decoupled from meteorology. So we are going back 12 hours or until an ice cloud forms. We can stop before, of course, or until we go below roughly minus 40 degrees. And there we stop, and the difference is that a microphysics model is run now forward. So you go back in time, you initiate your model using the methodology from era 5. Also, if you have pre-existing ice in era 5, this is also accounted for. And then you go forward in time running your model. So you are looking at the ice forming or sometime disappearing along the trajectory. So what we are getting at the end, when we are back to the satellite's overpass, we are getting what the model simulated in terms of microphysics and ice water content. It's a two-moment scheme. We are getting now how the ice formed heterogeneously, homogeneously, and you can also have pre-existing ice from the initialization point. And you also have, of course, the origin in situ and liquid. So I put all the configuration detail. This is mostly, again, for information. I mentioned it's a two-moment schemes. It has homogeneous freezing, heterogeneously freezing, the positional growth sedimentation. And yeah, this already mentioned. We are going 12 hours back in time. The methodology is still from era 5, but this time it's 6 hourly, not 1 hourly like FlexPart. And yeah, so some important things are that we, of course, need more because we are running the microphysics ourselves. So there will be a few things that we need to account for. I will mention again here the temperature fluctuation later. This is quite important. The INP concentrations, of course, we have to set it and some other quantities here, including the sedimentation factor. So because we are running in a Lagrangian way, we don't really know what's above and below. So you have to decide how much was the fraction of that you are losing compared to what you are gaining in terms of sedimentation. So the example will be the same as before. So you can still follow and compare later on the two methods. So here you have a quick view on the scene that I already showed on the right. So this one you know. Here you can see the overpass crossing the cyclone. That's the green area here. And we are looking at this bit of plain green from the center to the edge. So from point A to point B, you are going towards the right here. And yeah, so I'll be showing what's happening at point B, so at the edge. So that's the most aged parcel of the two. So what's going on here? So we'll take this example of point B, look in detail of what the method is doing, and then we can look at the results. So this I'll try to take it step by step. I think Atulia will explain it better than I, but I'll try. So we are starting here from 0, like before. So that's our overpass time. And we are going maximum to 12 hours, as I mentioned earlier. So that's our endpoints. And that is where the microphysics will start. So this is just the temperature from era 5 at 0, and the temperature increases because, well, we are going deeper, well, closer to the surface in that case. We have other informations. There is here the cloud water content from era 5, so we can, here we cannot see if there is liquid or not. It's not zoomed in enough, but yeah, there is pre-existing ice here. You can see that you have existing ice in era 5 when we start the simulation, so that will be called pre-existing ice. So this was era 5 purely, or initialization inputs, and bottom, now the second row will be the clamps ice environmental conditions. So the temperature is the same. What you're looking at the plain line here is the median of the temperature. And so why do I mention median is because, well, so we are running several back trajectories, and we are running the model several times, actually. Not the trajectories, but the model, the microphysics model is run several times. And why do we do that? Because we are including temperature fluctuations. So the temperature is fluctuating in a random way, but although controlled by a parameter, a temperature width. And so each of our ensemble member has an oscillating particle temperature around the median. So the median should look exactly like era 5 if you have enough members. We have 10 members here. But each member is fluctuating around the median or the mean here. On middle here, you have the relative humidity, and that's quite interesting. You can see if you look at the median of the relative humidity, it does not really trigger in orange here or yellow is the threshold for heterogeneous formation if you have available INPs. And the top one here is the cup line for homogeneous formation. So you can see that you need actually these fluctuations of temperature to increase in very shortly the relative humidity to allow for at least hitting the homogeneous threshold. And this is the INP concentration. Okay, so here we have the members. I will not discuss this one. And this is the Ni that is produced by the satellite. So if you look at from the initialization point, we didn't have much ice crystal number. This was corresponding to pre-existing ice. So you had the same ice water content as you had here, roughly. And initially, there is this phase one where we are losing ice water content. And this is deposition, well, or sedimentation or sublimation as well. Here we are losing ice water content. As we are losing ice water content, especially by sublimation, then this is releasing INPs that were in the pre-existing ice carried up from the liquid origin or the air mass that came from the lower, warmer region. So we are losing ice here by sublimation, but we are releasing at the same time, not only sublimation, also sedimentation, but the one that sublimates releases INP. So we have an increase in INP here. And at some point, as we are increasing the relative humidity through the process, we start to trigger homogeneous nucleation here. So the strong increase in Ni that you see here. And then, yeah, the INPs are decreasing. And then you just have more sedimentation appearing. So this is interesting, but it's quite tricky. As you could see, I'm also hesitating a bit. So getting all this information is a bit tricky. So that's why we developed this metrics. You can see these are the derived metric that correspond to what we actually want to take from this. So this is the ice origin. So in blue, you have pre-existing. This came from era 5, but it goes down quite quickly. As we started to form ice heterogeneously first, in the first part, yeah, that was where we used the INPs to create ice. Then this decreased as homogeneous formation triggered. So homogeneous can only be triggered when we used already all the INPs previously through heterogeneous nucleation, and then we hit the threshold for homogeneous freezing. So in the end, at the satellite overpass here, you could say, well, okay, I have zero pre-existing ice from era 5, that's fine. I have about 25% of the ice that I'm observing for this parcel that is formed heterogeneously and 75% that is formed homogeneously. So now we can finally attribute these metrics to the satellite observation. For the origin, well, we started liquid with the pre-existing ice, and now we are 100% in situ formed. This is the cloud age, the time since the formation. Okay, so we did all the work to go through and understand how this works. It was a bit long, but now we can just finally just look at what's the results along the overpass. So what we are looking at here is what's the state of my ice origin here, cloud origin, and cloud age at the green line. So what does it look like at this point? And that's what we are getting. So you can see here for the same cloud. So now it's limited to the cirrus area. So we are limited to below minus 37 degrees because that's a limitation of the model. So we don't see what's happening below, but this is just the cirrus region. We can see that the cirrus is formed of a mix of homogeneously and heterogeneously formed ice. In that case. So vertically, we cannot say really it's uniform. And most of our cases that we're looking at is like this. We have mixes of the two formations. We have some pre-existing near the front here, but it's disappearing quite quickly. The ice origin is then mostly in situ, except for this area here where we have some liquid origin, and then we have the edge here. So we could see the parcel is about 12 hours old at the edge, and of course, so the cloud is a bit. It looks less old than our FlexPart approach. So yeah, different results. We looked into statistics as well. I won't show too much here, but we did 3 case studies at this point. One with a slow updraft, which is what I just showed, one with a high updraft, and one orographic case. We could see that in most of the cases, most of the pixels that we observed were in situ formed, except for the high updraft, where we had a bit more liquid origin. The colors show the formation pathway, so heterogeneous in red and homogeneous in blue. And here we could see it's mostly shared. So it's important to realize there is a coexistence of the two formation pathways in the same cloud. And this is just in the series regime. We are not looking at the mixed phase. So yeah, a bit less for the high updraft where we have more homogeneously. Otherwise, it's rather 50-50. At least, we just have these 3 case studies for now. The method is a bit slower, but that gives us good hints at least. And yeah, I wanted to finish just on still the importance of input model parameters, because we are getting this, but you could tell me, yeah, that depends on the model that you're using, all the parameters, which one. So I totally agree that this depends on what parameters that you're used. So we, of course, compared to the satellites for validation, the top rows show the ice water content. This is not the easiest plot to finish with, but these are violin plots, so that shows you the distribution here, and it's symmetric on both sides with the median that is, so you can just focus on the median that is showed here. That will be sufficient for this talk. So here we have the median of the ice water content from the satellites, and in blue you have the median for the default method that we use. So you can see that it's a bit different for this case, but not that much actually. It's quite good. For the ice water content is the same. The median here is not, well, it's quite close to. So the model, at least it's not, we didn't really tune it, but yeah, the results are not too bad if you compare to the satellite. So this, again, is the simulations of Clam's ice, and this is the observation of the LiDAR radar. And we played around with a few parameters. I will just show 2 here. So the sedimentation factor, so that's the ratio between what you lose compared to what you gain at the top and the bottom of the parcel. This is for now parameterized. So the default value, if you turn it off, then the ice water content is increasing by a lot. And of course, it's quite sensitive. So you see that the ice water content is quite impacted by the sedimentation ratio. The ice crystal number, not so much, actually. But the temperature fluctuation is really impacting very strongly the ice crystal number as expected. That's where you can trigger or not heterogeneously and then homogeneously nucleation through the small scale fluctuation. So yeah, these parameters need to be well adjusted. And for now, we just, yeah, we don't really have much constraint on that, but the default value that we took were quite accurate, at least compared to the satellite. We looked a bit further, and this did not impact too much the metrics that we are looking at, so that was encouraging. Yeah, so that's the end for this method as well. So yeah, we managed to get this other method where we can run a microphysics model to get a bit further than the initial FlexPart approach. There are some metrics that are very important if you are tempted to use such method. The temperature fluctuation appear to be the most sensitive metrics to our origin information. And yeah, using ensemble was also quite necessary. So this first agreement, so for now we have 2 case studies, and yeah. So of course there are still issues. So the model parameters, as I mentioned, and also it's a much slower method than before, but we are working on that. Project is ongoing with Martina and other at Mainz and Jülich. So we are hoping to improve this and make it more usable globally. So that's my final summary. So yes, this Lagrangian method have a lot of, they offer a lot of opportunities for getting more information, and we are hoping to get this coupled in an operational way. So there are two methods right now. One fast one that we can get to get the first start information on the origin of the cloud, and then a second one that adds the own microphysics to get the ice formation processes. But again, you rely a lot of also, of course, on reanalysis. So that's our status. We were hoping to get this. That's what I will finish on. So that was our goal. So we do have that with just Lagrangian trajectory with FlexPart. We got the origin and the time since formation. And with the microphysics model, we also got the formation pathway. The two of them are not necessarily agreeing, and that is because some small scale processes, also time scale, are not well captured by ERA5, of course. So we saw that the temperature fluctuation, for instance, are quite critical in our Clamps ice approach, and this is not included necessarily in ERA5. So we see a lot more in situ origin in the method that uses Lagrangian microphysics compared to the other, and the time since formation, of course, responds in the same way. It's a bit, well, the series appear more aged if you are using just ERA5 compared to Clamps ice. I will tend to trust a bit more the one on the right, which is a bit more reasonable for this case, for instance, limited to 12 hours instead of more than 30 hours. But yeah, so there are still disagreements. We are working on that, but yes. So that's all. I finished with this sort of success slide, I hope, and to open the discussion. So I'm happy to answer any question. Just stop the recording.